Okay, we're still on chapter 6, and we're talking about the evolution of the terrestrial planets. We had talked about the terrestrial planets in the first video, the terrestrial planets versus the Ovian planets, which are the gaseous, bigger planets in the solar system. And we also talked about the fact that, let me just move this down. There we go. That the terrestrial planets had similarities, like they were all small and dense and rocky and metallic. And some of their differences included the fact that they had rotation directions that were different. Venus has a completely different rotation direction, and the fact that they rotated at different speeds. Those are some of the differences in terrestrial planets. And there were also differences in the presence of a liquid iron core or no presence of a liquid iron core. And that had to do with some of our talk about differentiation, which we'll review in a second. We also talked about differences in magnetic field and protection by solar wind. We'll review that in a second. And what that had to do with temperature and atmosphere of the terrestrial planets. And all of this seems to be related to the planetary energy rate. So the rate of losing and gaining energy. So let's explore the differences in this video. Now, just to go over a bit again and review, the core we know is generally a nickel or iron core for the terrestrial planets. And you see that right in the center, the orange core right in here, all right? In some cases, we have an inner core and an outer core, but in all cases in the terrestrial planets, we have a core. Some cores are bigger than others, of course. This is related to the first stage of planetary evolution, the differentiation stage. And when we talk about the differentiation stage, we're talking about melting the denser materials and sinking them. Well, what will melt the dense materials so that they will sink to the core? There's a few things that can contribute energy to the planet. And one is to think about formation of those planets. And this is about 4.5 billion years ago. This is after the Big Bang. And there are materials that form the sun and spin off and collect other materials from the Big Bang into our solar system. So we do have radioactive elements that are still revolving around our galaxy and can be incorporated into these planets that are forming now around our sun. And those radioactive elements can certainly provide heat to a planet. In addition, you have so much stuff in the area of our new solar system. You have so much space debris that there are a lot of hot collisions. And when we talk about hot collisions, we're talking about collisions with a lot of energy. So that all of these collisions can certainly melt denser materials. Then too, we have the sun. And the sun is continuously shining and providing some melting as well. And you have the formation energy of the material that is coming together to form these planets. So several of these, all of these, can melt denser materials and cause them to sink lower toward a core. Let's talk about which of these elements is most important and most long-lasting. Let me just move this over. There. So if we think about the radioactive decay of the formation elements that are flying around from the Big Bang, they are going to provide a lot of energy, at least initially. And we're talking 4.5 billion years ago. So these radioactive elements do have a half-life, and you could say, well, that half-life is very long. Yes, but it's not 4.5 billion years long. So there is a half-life, and this radioactivity will peter out after a few million years. Now let's go to the hot collisions. The hot collisions formed from all the space debris after the Big Bang certainly provided a lot of energy to these developing planets, but it's short-lived. You have a collision and then the extra energy can radiate out into space because everything radiates from a high energy area to a low energy area. So those hot collisions, very powerful, but short-lived. The sun, of course, is there from the beginning of the formation of the solar system, and it is there continuously. But when we think about it, it's relatively low power compared to having nuclear fission right on top of your planet. The sun is relatively low power when we compare it to radioactive decay. When we compare it to massive asteroids and space debris colliding with our planets, the sun's continuous energy is relatively low power. Now, let's talk about the fourth one, the formation energy. And that includes all the energy that went into the material and the mass that formed this planet to start with. And that was 4.5 billion years ago. And if you can get that very dense, very heavy elemental debris down into the core, then it can hold a lot of energy and continuously radiate it. It could be a very powerful source of energy for an extremely long time. Think about the core of the sun. It is literally going to last us about 4.5 more million years after it's been going for 4.5 billion years. So we've got a ways to go because in the sun, the densest material is in the core. And like we talked about, it takes a photon hundreds of thousands of years to get out of the core. So this is a very long-term energy source if the dense part of your energy is tucked in your core. Well, when we talk about that, the formation energy, what determines if the formation energy of the planet gets into the core? And you might say, well, what have mass and energy got to do with each other? And then we bring in Einstein, because Einstein said E equals mc squared, which means energy equals mass times the speed of light squared. C is the speed of light squared. And in doing so, Einstein brought together the particle and the wave form of energy, just as an aside. But to get back to it, if we look at E equals mc squared, it means that the larger planets, which have more mass, are going to have more energy because they have more critical mass that is a real storehouse for that energy. And in fact, if you look at that, which terrestrial planets are largest? Well, over here, we've got certainly Venus and Earth. Maybe Mars can qualify. The smallest terrestrial planets are Mercury, and the moon is not a planet. The moon is a body. Let's say the smallest terrestrial bodies are Mercury and the moon. So if you look at this, we see in here a very hot core to the Earth, and it's got a solid, hot inner core and a liquid, very hot, outer core. And with Venus, we do have a solid inner core, not quite as hot as Earth, but it's there, and we do have an outer core. With Mars, we believe that Mars started with a hot inner core, just like the Earth. And this is where I needed to check on your book a bit, because your book isn't really that up to date on this. So now, due to some probes that have landed and been in the atmosphere of Mars as early as 2015 and 2016, we are saying that Mars did have an inner core just like Earth at one point. We'll go into that a little bit more. When you look at Venus and Earth and maybe Mars, you would expect that inner core to retain heat and to retain its liquid qualities in the inner core. Excuse me, I'm going to change that slide. I'm going to change that. It's going to be a solid inner core and a liquid outer core. Sorry about that. That's going to be changed. We would also expect to develop a magnetic field based on the liquid outer core. Because remember, we talked about the rotation and the spinning of this metal that can cause an electric field and then cause a magnetic field and then cause an electric field and confer solar wind protection on the Earth. So we would expect that these big planets of Venus and Earth and maybe Mars would have a magnetic field and solar wind protection. Now, your book will tell you that Mars never had a magnetic field, and that is a very controversial point because the latest data coming out says, yes, Mars did have a magnetic field. We'll go into it a little bit more. You would also expect these bigger planets to radiate heat from the inner core to the outer crust. Remember, all energy goes from high levels to low levels. This is going to radiate if you've got a very warm core, just like in the sun. So as a result of that, you can expect this hot rock in the mantle to become geologically active. It's going to become magma. It's going to become what can come out as lava on Earth. And while we know that this is the case for Venus and for Earth, we're now beginning to understand that this was the case for Mars as well. Now, that was all in the first stage of planetary evolution. The second stage of planetary evolution, after you formed the core and the mantle and the crust, was that everything got bombarded by the rest of the space debris that was in the area. And in addition, there's some talk that the debris from Neptune and Uranus also contributed to this bombardment. But the second stage of planetary evolution impacted all of the terrestrial planets and caused enormous craters in all of them. And in fact, that heavy bombardment lasted for about 700,000 years. And it was due to the debris and to the asteroid fields that were tucked in between the terrestrial planets and the Jovian planets, but they really impacted the terrestrial planets. And they produced craters. They probably produced our moon and certainly the moons of Mars and other terrestrial planets. How did this, besides cratering, how did the bombardment impact the crust and the mantle of the terrestrial planets? Well, it had a secondary effect as well. In that bombardment and in those massive craters, some of those craters went beyond the continental crust and straight into the mantle. And when they got into the mantle, suddenly they were getting close to sources of magma. And magma is the heated rock of the mantle that's heated by the core rising up with its radiated heat. When you see volcanoes and when you see lava, you are not seeing lava, you are not seeing plasma from the core of the Earth. You are seeing heated rock or magma from the mantle of the Earth. Some of these craters went down to that level, unleashed this magma, which came up through the cracks in the crust and smoothed out the craters by giving a smooth layer of lava over the crater. As a result of that, we had large basins on some planets, particularly Venus and Earth, and in some cases Mars. Those basins on Earth became our oceans. So that bombardment had a way of manipulating our crust and our mantle with lava. I want to go over one other thing, that you see a lot of smoothing on the larger planets, but on Mercury and on the moon, very cratered because they're cooler, they did not have magma as much. See on the other side.